basically bring it into the category of small oscillations, and we can analyze a system under small oscillations using different mathematical techniques. And in this unit we are going to do that. The first topic that we actually start with is called equilibrium condition. So any system more or less wants to be in its equilibrium condition, and sometimes there is no force acting on that particular system and it is at complete rest. We usually call it as equilibrium. Well, the definition remains the same, but there are certain mathematical analysis that we need to do, and also we need to understand that there are two kinds of equilibrium. Okay, one is stable and one is unstable. So these things we are going to just make clear. Okay, and this will be actually the topic for today. Okay, so let's say you are basically having a system and you are given a potential, let's say. Okay, so maybe the given potential that we have is Vx. Okay, Vx is the given potential, and we can actually expand this potential. So we basically have from Taylor series, as I told you yesterday that you have done your mathematical physics and we did study about Taylor series and all. We can actually put these Taylor series idea and all into um, application. Okay, now this Taylor series, okay, we are basically going to do it for small displacement. So this Taylor series expansion we can actually do it for small displacement. If we in fact look into the Taylor series expansion, we know that we are going to take some differences there, and that difference needs to be very small, and that is where we are actually going to talk about small displacements. Okay, so if we remember Taylor series expansion, what we have is we basically have a function. Okay, and that function can be expanded. Okay, uh, about a point. So let's say we are going to expand it about a point x is equal to x naught. Okay, if you don't remember Taylor series, you can just refer to mathematical physics class. We have just done it last to last week, I guess. And then you basically have it as x minus x naught. When we did the Taylor series expansion, we have written it as x minus a at the point around which we are expanding. So we are expanding it around x naught, so I'm just written it as x minus x naught divided by factorial 1. Okay, and then I can write it down as dv dx, right? And take a total derivative. If it's only a function of x, it may be a function of x, y and so on, so I can just take a partial derivative as well sometimes, but it's okay. Right now I'm just taking it to be dv dx at x is equal to x naught again, and then I'll keep expanding and I will add one more term to it. Okay, the next term, if you remember, is x minus x naught whole square divided by factorial 2, or I'll take the total derivative, t square v dx square, right? And then that is also x is equal to x naught, and then what I can do is I can keep on writing the remaining terms. Okay, but we are talking that this x minus x naught is a very small difference, maybe in decimals. So if I take x minus x naught square, it will be even smaller, and if I go further, I'm going to get even smaller values. So what happens usually is that these values will keep on reducing. So if we go too far also, it doesn't make of much of sense. Okay, for example, let's say x minus x naught, okay, x minus x naught, okay, is 0.1, let's say 0.1. So that means if I take x minus x naught square, that means it will be 0.1 square, so it will be 0.01. okay, and then if I take x minus x naught, let's say cubed, okay, so that means it will be 0.01 into 0.1, so it will be 0.001. So what happens is this keeps on reducing and becomes more and more insignificant, as a result of which I'm not going to do it. Okay, next what we're going to do is we are going to trying to analyze this particular expression, and for that what we can say is we can actually take a point here. Okay, so let's say I'll take origin, okay, origin as a reference point. So maybe x naught is the origin and we can take this as the reference point. Okay, so take origin as the reference point. That means if I x is equal to x naught at the origin, this value would be more or less 0. So there is no change at that particular point. Okay, And now if you remember your concept of maxima and minima, so let's say I want to do this for maxima and minima. We are going to use numerical problems to understand this better, but let's just look into the main theory here. For maxima and minima, you know that this value of dv dx, the first derivative of dv dx, okay, at x is equal to x naught is equal to 0. So if you basically have a function, forget about potential. If you have any function, if you want to find out the maxima or the minima, which you might have done in your class 11, 12, okay, if you take the first derivative, if that is the 0, okay, and you whatever value you get, whatever function you get, okay, and you equate it with 0, and you can find out at what point you have the maxima, at what point you have the minima, okay. So that is very important, okay. So if we just consider this now, okay, and we have also said that that uh, x is equal to x naught at is equal to 0. So we are taking just the reference point, okay. So there is no change as such. So therefore what we can do is we can write down this vx, that means potential as a function of x, which we have expanded by Taylor series as this term will become 0 because dv dx is equal to 0 at points of maxima and minima, okay. And x is equal to x naught is equal to 0, so that means this function will also become 0 if it's a pure function of x, right. So what we do here is we can just simply write it down as 1 divided by factorial 2, so that means we just have got the final term here, and we are saying that this x naught is equal to 0, so that means this will be just x square, okay. So I can just simply write it down as x square, okay. This is just analyzing this particular expression when we are going to find out the maxima and the minima. I'll tell you why we want to find out the maxima and the minima, okay. So we are going to take this, okay. So there are this is the simple expression that we get after doing the Taylor expansion of any potential when we are talking in terms of small oscillation, okay. You have to understand this, and in this case what we say is that x is equal to 0, okay, and then the higher order terms, okay, given you the reason of 0.1 and 0.001, okay, can be neglected. We can actually neglect the higher order terms, okay. And when we talk about x is equal to x naught,
Hello, sir.
okay, that means we are talking about a point which is called stable point. So this is a
Sir?
stable point. Why do I call it the stable point? See, this is at the origin, okay, basically having no changes as such, okay. So x is equal to x naught, we call it as the stable point, but I'm going to explain you stable point now, okay. So don't worry, I'm going to explain you stable point so
Hello,
that it's
hello,
a bit
sir.
more clear to, yeah.
सर रिकॉर्डिंग नहीं हो रहा है आज.
Recording नहीं हो रहा है? No, no, I have put it on recording, I guess. No, it's getting recorded.
Okay, sir. Sir,
Yeah, it's getting recorded, okay, no problem. Yeah.
sorry, sir. Sorry, sir. Sorry, sir.
Okay. No, but it's okay, you should be aware, right? मेरा गलती हो सकता है, recording करना ज़रूरी है because this lecture is actually not on YouTube, so I need to put this also, that's very important, okay. So we're discussing small oscillations, so that means that whatever we have analyzed in the last page, in this page, okay, we are going to actually have this applied in small oscillation, this particular case, okay. So to just remember this, that's very important. So let's just write down one sentence here, okay, before we proceed to understanding stable and unstable equilibrium. So if we just say for, let's say, small oscillator, okay, so it's not a very complicated term, okay. Small oscillator, we basically have it as Vx, okay, and for small oscillator specifically we can actually mention, I've already written that but I'll again write it down, higher order terms can be neglected. Now why? Because small oscillation, so that means the change in the original position and the new position, okay, will be very small in order. So that means if I go square, cube and all, it's going to get smaller and smaller, and as a result we can always ignore the higher order terms, okay. So we can just write it down as Vx is equal to half x square, okay, and then d2v dx square x is equal to x naught. Okay, so this is the most important relation that we have right now in our hands, and I will just mark this as number one. Okay, we're going to use it, but before that I will just give you some note of stable and unstable equilibrium. Although I'm writing it as a note, but don't consider this as insignificant for exams, it might be there also. Okay, so maybe what I can do is we can just have a kind of system where we actually going to study a simple harmonic motion, let's say. So maybe I want to study SHM, and when we study SHM, what we do is we know that this is going to be a motion which will have some kind of symmetry, right? Let's say it is basically a sine curve or a cosine curve, okay, and this is the motion that we actually have. Okay, so in general what we do is when we actually plot the graph, along this x-axis we plot the displacement, and along the y-axis we actually will plot the potential, let's say. And if you see that the displacement is actually a periodic function of x, we generally say that the motion is simple harmonic in nature. Okay, the motion is simple harmonic in nature. So if you look into such systems and we analyze this, okay, we basically have got 2 points here that we need to understand. This is the first point and this is the next point. Okay, and this particular point, okay, if you remember, is basically called as the maxima. Okay, and we know mathematically the condition how to find it out, and this is actually a point of stability. This is stable, and this particular point is actually a point of minima, and this is also stable. Now in both the cases we basically call that uh, the system is stable. Now what do I mean by stable here? See, you may play marbles, okay, if you know, if you have played marbles when you were a kid, okay, or even if you have not played, you do understand that the marble is being thrown and it is actually put into a hole kind of thing. Okay, you basically dug some hole in a mud, and then probably you can just put the marble in there, and then the marble will just go inside and sit here and will be here. Okay, so even if there is some kind of force being applied this side or that side, it is basically going to come back and sit here itself. Okay, so the stability that the marble has at this particular point is more. Okay, so this is basically called actually the stable equilibrium. Okay, and this what we call is, okay, okay, so imagine the marble is here, so this is stable. Now if the marble is here, okay, it will be still there. Okay, it will be there, no doubt, but if a slightest of force is being applied, it will start coming downhill, might be on this side or might be on the other side. So that means this is also stable at this particular point, but when we go either on this side and this side, this basically is going to just go to an unstable state. Okay, so in general maybe this particular position is stable, but when we talk in terms of equilibrium, this will be the position of unstable equilibrium. Okay, and this will be the position of stable equilibrium. So remember this word equilibrium here. Okay, this may be in equilibrium, but this will be more of less stable, and this will be more a position of instability. Okay, so maybe I can just replace this word of stable as unstable. It's in equilibrium, but then it's still in unstable state. Okay, so if we just imagine another example, maybe this potential graph that we all have come across. Okay, like this is also a potential graph. This is also something which is having a similar idea, right? We have got a point here which is the minima, and we have it as stable equilibrium. Okay, equilibrium. Imagine again maybe a pendulum. That is also a good example of simple harmonic motion, right? So this is also a simple harmonic motion example. So we have the pendulum bob here, okay, and it basically will keep on oscillating from one position to the other. So as soon as it goes to this end or this end, momentarily it's in stable equilibrium. If you plot the graph, you get the position of maxima and minima. Okay, and these are the 2 points that we have. Okay, this point and this point, not this point. Okay, this point it will have maximum energy to go either on this side or this side. Okay, if we think about, oscillations not at rest position, when oscillating positions are there, so this point won't signify any kind of equilibrium, but this particular point and this particular point, if you actually plot a graph, you're going to get these kind of graphs, and there you are going to see that there will be two positions of equilibrium. Okay, so these all are examples of simple harmonic motion, and if the oscillation is very small, we can actually bring it under this category of simple, harmonic motion and equilibrium states. So what I'm going to do is we're going to just look into certain expressions that we already know. So in general, if I just say for simple harmonic motion, okay, we basically have F, so that's the force, and this will always be minus of kx. Okay, and we all know that this is actually called the restoring force. Why it's restoring force? Because if a body is in maximum displacement position, it will come back, try to come back to the original position, and the force by which it comes back will depend on this. Okay, so this is actually called the restoring force, right? So maybe I can write it down here. This is your restoring force. So although these concepts are something which you already know, but then we are going to use these ideas, okay, again and again. So with the help of this force, okay, you may have a particle. Maybe I can talk about that example of the marble inside the hole. Okay, it will may keep on oscillating, but at the end it will come back to at the center position. Okay, so tries to come back to mean position. So that's the importance of restoring force, mean position. Let's just remember this. Okay, that's very important. On the other hand, if we just talk about the potential here, okay, we know that the potential and the force are connected. We have seen the relation so many times. So if we just want to find out the potential, we can just simply write it down as half k x square, right? So all of us know that F is equal to minus of dv by dx, right? So you just take this and then you can get it, right? Um, so some constants will be involved, okay, and then if you do the calculation, it will be half kx square. You have to just recall this, okay. This is something which you already know. So if you know the force acting, you can actually find out what is the potential. That's it, okay. And then we can actually compare the relation 1 and 2. If you remember, if we have done it already. So in the previous relation we have seen this was our relation 1. Here also it's Vx, but here we are talking about small oscillation, and if we are talking about a restoring force which is acting in small oscillation, both these potentials should be same. Okay, so it's under the condition that both are actually undergoing small oscillation. So the Taylor series result that we actually got for small oscillation, you might not have equated it with half kx square, because it's not needed, because other cases we might not be talking about small oscillations, but here we are talking about small oscillations, so we can actually connect them both. So both 1 and 2 will represent the same quantity. So in that way, if we just compare it, v is equal to half kx square and v is equal to x square divided by 2 into del square v del x square, and if we just compare that, we actually can find out what is the value of the force constant. If you remember, k is also called the force constant, and that is actually a constant which is responsible for bringing in, or how much, or it can give you the idea of the magnitude of the force that is acting, the restoring force magnitude. So if you just take this, I can just simply write it down as d square v dx square at x is equal to x naught. If you want to solve any numerical problem, okay, you have to remember this. This is very important, okay, important. Maybe just I can mark this. So when you get those questions, maybe in entrance exams and all, they usually ask this, okay. They won't give you this condition, you have to know it, and you can find out the value of this constant k if you just take the potential and differentiate it twice. I've derived it here so that you know that why you should differentiate twice the potential to get the force constant k. That's the result that we actually use, okay. So it's a very basic idea, but it's again very important. And what is x naught? X naught, can be the value which is actually at minima or maxima. Okay, minima or maxima. So this is important. So this is actually the main theory of equilibrium. Okay, and if you know what is k, you can actually do a lot of things. Okay, we already know what is k now. Maybe I can just put it inside a box. This is important, as I said. So when I ask you these kind of questions in exam, you should know the theory, and then it'll be more comfortable. There may be a tail to the question. How do you get k is equal to d square v dx square? So you can just give this argument. Please try mentioning small oscillation. Important. So now we actually can find frequency and everything else. So if there is an oscillation, there must be some kind of frequency involved. So we can easily find out the frequency. Okay, and this is your angular frequency is equal to root over k by m. Done it. You might have done it a number of times. You can also find out the linear frequency if you just write down omega is equal to 2 pi f, right? This is 2 pi f, so you can just put it there. You can find out linear frequency. If the question mentions only frequency, find out f, just divide it by 1 by 2 pi. Okay, and if the question mentions angular frequency, just root over k by m. That's it, right? You can also find out the time period, because frequency is 2 pi f, or it may be written as 2 pi divided by t. Okay, so you can find out the time period also. So whatever quantity is asked in a question, you can easily find it out. Okay, let me just talk a bit about equilibrium. Okay, before we proceed, let me just talk about this equilibrium, which is important, and I will give you a few points that you should actually remember. Okay, uh, equilibrium. So if we talk about a system to be equilibrium state, that means there is no external force that is acting. No external force, okay, acts on system. So that may be a simple definition of equilibrium. So if someone asks you what is equilibrium, you say no external force acts on the system. F is equal to 0. External force, remember this. Okay, there might be certain forces which are acting within the system. There are molecules and all. If they are actually continuously there, that will be there. Okay, so you cannot bring it under this equilibrium state. So you have to understand this. No external force.
Hello, sir.
So yeah,
Sir, no external force we cannot say, na. Sir, external force can be balanced by
yeah, yeah,
other
exactly.
factor.
The thing is, no external force acts in the system. It means that the total force acting on the system should be zero. The total external
Um,
force.
Yes, an external force can be balanced by other forces, right?
Yeah, we can balance it. Okay, and then we can actually say that the system is actually in a stable state. We can do
Yes.
it. Okay, okay. So we can actually say this is actually stable, or maybe we are basically having an unstable state. Okay. So if we do it in stable and unstable, whatever I have discussed, let me just give you the gist here. Okay, in stable state, whatever may be the maxima or the minima will be equal to 0, and this f is equal to 0. And here also is the same case. Okay, now you understand what is a stable and an unstable state. I've already explained. Both are equilibrium, but one is stable, one is unstable, right? So if we just take this example of a marble being at the peak here, or a marble being here, this is stable. Okay, this is unstable. Okay, so this is the example, but in both the cases these conditions will more or less remain the same, and we will know that how to actually find out whether it's at the unstable equilibrium or the stable equilibrium. Okay, the potential energy will be actually minimum. So when we talk about stable equilibrium, the potential energy will be minimum. Okay, in unstable equilibrium we can actually have the potential energy to be maximum. Okay, we're going to look into it. Okay, we're going to give some examples and explain it to you, and then the second derivative, if you find out, which will actually give you the value of k. Okay, I've already told you. This d square v dx square will be positive, and if you get the value to be positive, that means we are actually having a position of stable equilibrium. This is mathematically, okay. And then if you plot a graph and check it, you will see that yes, in fact, it actually gets that point. Then d square v dx square is equal to negative. So if it is negative, this second derivative of the potential, it will be a position of unstable equilibrium. Now these things may not be very clear until and unless we actually do some numerical problems. Okay, so that's important.